So we are going to continue the practice session as we started yesterday. Uh, I told you the distinction between Gauss-Jacobi method and Gauss-Seidel method yesterday. And I said that Gauss elimination, Gauss-Jordan method, etc., just matrix based. Now I'll tell you just orally to tell you the difference between Gauss elimination method, which we did a lot in the class, and certain Gauss-Jordan method. What I emphasized a lot in the class, which I'm reiterating now, is that in this, we are just trying to convert it into an upper triangular matrix, which is like the row echelon, reduced row echelon matrix. But when that is, you get a matrix like this, 0 everywhere here, and the last row can be reinterpreted as z is equal to something. Let's say if there was a 3 here, 3z is equal to, let's say there was some 7, 3z is equal to 7, so z is equal to 7 by 3. Put that z value in the second row interpretation, you will get something into y plus something into z equal to some number, let's say 11. And we already know the z value, so you will get the value of y. Then you'll have another number here. So you will rewrite the first row as an equation form. You already know x and y, so substitute that. You have numbers here, and you will get, say, let's say there's some number 9. So let us just assume that these numbers are 1 minus, let's say minus 1, 2, and 3, just as an assumption. So minus 1x plus 2y plus 3z is equal to 9 is the interpretation. Now 2y, you can substitute the y value. 3z, you can substitute the z value. And you will get the value of x also. There is a story about Gauss elimination method. But in Gauss-Jordan method, what we get is the reduced form will be an identity matrix. That means you will have 1 year, 0 year, 0 year, 1 year, 0 year, 1 year. So you can directly say that 1 times z is equal to something. So you get the value of z. 1 times y is equal to something. So y you'll get. 1 times x is equal to something. So the fact is that in the Gauss-Jordan method, you, by similarity operations, by row operations, you get a unit matrix 1 0 0 0 1 0 0 0. Sorry, there's a confusion about you. This is more popularly called as identity matrix. Okay, so that's about Gauss-Jordan method. Now, I will switch to analytic geometry, solid geometry. I did do a lot of problems in the last few sessions, but not many students were present there, so I wanted to recap some of those problems. So let's have a problem like this. Find the first of all, okay, let me erase this. Show that the lines . L1 is the first line, x plus 3 by 2 equal to y plus 5 by 3 equal to z minus 7 by minus 3. And the line L2, x plus 1 by 4 equal to y plus 1 by 5 equal to z plus 1 by minus 1. Show that these L1 and L2 are coplanar. That's the question. And also find the equation of this plane. The plane containing these two. Okay. So now we use the condition that if L1 contains the line L2, then the condition is that you have this, whatever I wrote in the first line, x plus 3, y plus 5, z minus 7. In principle, what this means is x minus x1, y minus x2, z minus z2, where x1, y1, z1 are lying on L1. Okay, that is the first row. The second row will have direction ratios of the first line, meaning 2, 3, minus 3. The third row will contain direction ratios of the second line, namely 4, 5, minus 1. This should be 0. This is the condition for the two lines to be coplanar. So this leads to the equation. What this condition says is that this determinant is equal to 0. So this leads to 6x minus 5y minus z is equal to 0. You can check it out. X plus 3 times minus 3 plus 15 minus 5 plus 5 times, this is plus 5, okay, times minus 2 plus 12 plus z minus 7 times 10 minus 12 equal to 0. That if you simplify it, turns out to be this. Okay, let us give a name to this equation A. Now, see, the second line given is x plus 1 by 4 equal to y plus 1 by 5 equal to z plus 1 by minus 1, which means this is of the form x minus x2, y minus y2, z minus z2. If this has the line x2, y2, z2, this has a point x2, y2, z2 on this, that x2, y2, z2 is given by minus 1, minus 1, minus 1. So put minus 1, minus 1, minus 1 belongs to L2. Substitute in A. Substitute in equation A. So 6 into minus 1, minus 5 into minus 1, minus z also you substitute minus 1, equals to minus 6 plus 5 plus 1, which is 0. So which means the point in L2 satisfies the plane. Therefore, indeed, the L1 and L2 are coplanar. Had they not been coplanar, then the second line ka point will not lie in this plane that I constructed, right? So because in this plane, this point is satisfying equation A, therefore we are reconfirming that the two lines are indeed coplanar. Now, what is the second part of the question? Find the equation of the plane. Not only we have to prove that they are coplanar, we also should find the equation of the plane, and we have already found out by the determinant condition. By determinant condition, equation A, namely 6x minus 5y minus z is equal to 0, is the required equation of the plane containing L1 and L2. Containing L1 and L2. So like this, two lines are given, coplanarity is understood. Also, there's a very important aspect which I emphasized a lot in the class. That is, two lines are given. We have to find the shortest distance between them. So we'll call P1 as the point on the first line, P2 as a point on second line, such that the line joining P1, P2 is the shortest distance. So remember, even in class, I tried to make you imagine these lines may be skewed, may not be coplanar. So in the second problem here, which I'm stating, the two lines may not be coplanar. Yet you should find the shortest distance between these uh, the two lines. Obviously, they're not meeting. If they were meeting, then the shortest distance is 0. So we're assuming that the two lines are not meeting, not intersecting. Okay. So let me state the problem in full detail. Find the equation of the line of shortest distance and also, I should say also, and also find the magnitude of that shortest distance. Also find magnitude of that distance. Of the two lines. And sometimes the lines are not given in symmetric form. You should convert them. Okay. So here I already have given symmetric form. X minus 8 by 3 is equal to y plus 9 by minus 16 is equal to z minus 10 by 7. And L2 is x plus 5 by 3 is equal to y minus 29 by 8 is equal to z minus 5 by minus 5. Okay, so these are the two given lines, and this is what we have to find. Okay, so in the class I had given a method. You can try to see that, and there is another method. I mean, basically you have to find uh, a point here, and then find the foot of the perpendicular, this line to this line. And then if you join the foot of the perpendicular, you'll get the shortest distance. That's the method. I'll give you another easy method here. And that's why I thought I'll emphasize in this practice session. If you like this easiest method, you can find it. You can use this method. So let me take this L1 uh, as lambda. The ratio x minus 8 equal to 3 equal to y plus 9 by minus 16 is equal to z minus 10 by 7 equal to lambda. This is the an arbitrary constant I put. Similarly, let x plus 5 by 3 equal to y minus 29 by 8 is equal to z minus 5 by minus 5 equal to, let's say, xi as the another constant. Now, by equation of L1, we get an arbitrary point on an arbitrary point on L1, let's say it is P1 only, B will be of the form x1 equal to 3 lambda plus 8. See, 3 times lambda plus 8. x2 equal to, sorry, I made a mistake. Yes, I'm talking about this y. So this y, I'll make it as y2 because it's a fixed point that I'm talking about. Y2 is equal to minus 16 lambda plus 9. Is it plus 9? Minus 9, sorry. And Z2 equal to minus 7 lambda plus 10. See, this minus 10 will go that side as plus 10. Okay. So this is what I assume this point to be, having the coordinates 3 lambda plus 8, minus 16 lambda minus 9, 7 lambda plus 10. So if you uh, get hold of the lambda according to the condition that this is perpendicular, etc., then we will exactly pinpoint what is a concrete point here. This is still not concrete. Unless we put the value lambda, we don't know x1, x1 again. I'm sorry for this sloppy notation. X1, Y1, Z1 is my X1, Y1, Z1 is my point P1. Okay. Similarly, you have noticed what I've done for the point on L1. P2 will be X2 equals 3 xi plus 15. Y2 will be 8 xi plus 29. Z2 will be minus 5 xi plus 5. Now, if we consider these two coordinates, and if we know that this P1, P2 segment is perpendicular to L1 as well as L2, with this condition, we can indeed get the exact. One second, there's some issue with. Yeah, we will exactly point out what is your lambda at xi. So this line P1, P2, this whatever this line segment is there, this entire line will have direction ratios as x2 minus x1, y2 minus y1, z2 minus z1. Therefore, it will be precisely if you find the difference between these two, you will get, I think I have not done x2 minus 1. It's all the same. X1 minus x2 I would have done. 3 lambda minus 3 sorry, I'm using Cheta. No, sorry. 3 lambda minus 3 xi minus 7 minus 16 lambda minus 8 xi minus 38, and you'll get 7 lambda plus 5 xi plus 5. Mind you, it's not x2 minus x1. I mean, we are used to writing x2 minus x1, but I will rather say it's all the same. X1 minus x2 also will be done. Y1 minus y2. Z1 minus. So it will be basically the direction ratios are proportional numbers. It doesn't matter whether we take x1 minus x2 or x2 minus 1. They are separated by a sign. So yeah, so these are the three direction ratios. Using them, we get 3 times. Let's say this is A1, this is A2, this is A3. 3A1 minus 16A2 plus 7A3 should be 0. Why? Why? Because 3 minus 16 and 7, remember, are the direction ratios of the line L1. Therefore, I'm using these 3 minus 16, 7 with the new direction ratios of P1, P2 to get 0, because that's the perpendicularity condition. And similarly, using the direction ratios of the second line, namely 3, 8, minus 5, you get 3 times A1 plus 8 times A2 minus 5 times A3 is equal to 0. Because they are positive. 3, 8, minus 5. Okay. One is 3 and 8 are positive. The third one is negative. So solving this simultaneously, solving this system B, we get, by the way, these two equations involve lambda and zeta. Okay. Or that is, sorry, we get lambda and psi. That is, what I want to say is 3 times 3 lambda minus 3 psi minus 7 minus 16 times minus 16 lambda minus 8 psi minus 38. I'm substituting these values A1, A2, A3. Okay, don't get confused. Plus 7 times 7 lambda minus plus 5 psi plus 5 equal to 0. This is my equation 1 in the system B. Also, 3 times 3 lambda minus 3 psi minus 7 plus 8 times minus 16 lambda minus 8 psi minus 38 plus 5 times 7 lambda plus 5 psi plus 5 equal to 0. So these two, I'm putting it in orange. This is the first equation, this is the second equation. These two simplify to 157 lambda plus 77 xi plus 311 equal to 0. And sorry, what happens for the second, I said the second orange line I've written, that will simplify to 11 lambda plus 7 xi plus 25 equal to 0. Well, the numbers coming up are huge, then I cancelled and then I got this. So if you solve this, we get lambda equal to -1, xi equal to -2. Now substituting back the value of lambda and xi in P1 coordinate and P2 coordinate, we finally get, therefore, P1 equal to 573 and P2 coordinates will be 9, 13, 15. So now, because you have P1 and P2 are the coordinates, P1 573, P2 9, 13, 15. It's easy to get the distance. That is the shortest distance. And therefore the magnitude P1, P2 segment is 14. You just confirm that. So that's your easy method according to me. So I'll end the practice session here. Thank you.